Hello students, today we are going to discuss magnetic effect of current. In this, we are going to discuss Lorentz magnetic force, Fleming's left hand rule, force on a moving charge in uniform electric and magnetic fields, force on a current carrying conductor in a uniform magnetic field, force between two infinitely long parallel current carrying conductors, definition of ampere, then torque experienced by a current carrying coil in a uniform magnetic field. So let's start with Lorentz magnetic force. So it states that a current carrying conductor placed in a magnetic field experiences a force, which means that a moving charge in magnetic field experiences force, and that is given by Fm is equal to Q into V cross B, or we can write force on charge particle, that is Fm is equal to QVB sine theta n cap, where theta is the angle between velocity vector and magnetic field B. Now, if the charge is at rest, so the velocity of the charge particle is 0, then force on that charge particle is 0. So, a stationary charge in a magnetic field does not experience any force. Now, if theta is 0 or 180 degree, that is, if charge moves parallel to or anti-parallel to the direction of magnetic field, then Fm is equal to 0, or the force on charge particle is 0. In the next case, if suppose theta is 90 degree, that is, if the charge moves perpendicular to the magnetic field, then the force is maximum, and that is given by Fm maximum is equal to QVB. Since sin theta is 1, so you get maximum force is equal to QVB. Now, Fleming's left hand rule. If the central finger, forefinger and the thumb of left hand are stretched mutually perpendicular to each other, and the central finger points to the direction of current, the forefinger points to the direction of magnetic field, then the thumb points in the direction of motion, or you can say force on the current carrying conductor. So, force on a moving charge in uniform electric and magnetic field, when a charge Q moves with velocity V in region in which both electric and magnetic field exist, then the Lorentz force is given by F is equal to QE plus Q into V cross B, or F is equal to Q into vector E plus V cross B. Next is force on a current carrying conductor in a uniform magnetic field. So the force experienced by each electron in the conductor is given by, again, the Lorentz force F is equal to QVB sine theta. So we can write F is equal to minus E into vector VD cross vector B. If n be the number density of electrons, A be the area of cross section of the conductor, then number of electrons in the element dl is NaDl. So the force experienced by electrons in dl is dF, which is equal to NaDl into minus E vector Vd cross vector B, which can be written as minus NeA Vd into dl cross B, or this can be written as I into dl cross B, where I is equal to NeA Vd, and negative sign represents that the direction of dl is opposite to that of Vd, that is drift velocity. So we can write F is equal to integral of dF, which is I dl cross B, or F is equal to I L cross B, or we get F is equal to BIL sine of theta. The next is force between two parallel infinitely long current carrying conductors. So suppose if we have two wires of infinite length having current I1 and I2. So the magnetic field on RS due to current in PQ can be written as B1, which is given as mu naught I1 upon 2 pi R. And the force acting on RS wire due to current I2 through it is force on second due to 1, which is mu naught I1 upon 2 pi R into I2 L sin theta, or force on second due to 1 is mu naught I1 I2 L upon 2 pi R. B1 acts perpendicular and into the plane of the diagram by right hand thumb rule. So the angle between L and B1 is 90 degree. So L is length of the conductor. In the same way, magnetic field on PQ due to current in RS is B2, which is mu naught I2 upon 2 pi R. So the force acting on PQ due to current I1 through it is force on 1 due to second is equal to mu naught I2 upon 2 pi R I1 L sin 90 degree, or force on first due to second can be written as mu naught I1 I2 L upon 2 pi R. The angle between L and B2 is 90 degree and B2 is emerging out. So force on 1 due to second is equal to force on second due to 1, which is equal to F, which can be written as mu naught I1 I2 L upon 2 pi R, or force per unit length of the conductor can be written as F upon L is equal to mu naught I1 I2 upon 2 pi R Newton per meter. Now, by Fleming's left hand rule, if we see these two figures, if current is in the same direction in the first figure, so by Fleming's left hand rule, the conductors experience force towards each other and hence attract each other. And in the second figure, in both the wires, the current are in the opposite direction. So by Fleming's left hand rule, the conductors experience force away from each other and hence repel each other. Now, what is ampere? So the force per unit length of the conductor is given by F upon L, which is mu naught I1 I2 upon 2 pi R Newton per meter. So when I1 is equal to I2 is equal to 1 ampere and R is equal to 1 meter, then the force F is equal to 2 into 10 to the power minus 7 Newton per meter. So 1 ampere can be defined as that current which is passed in each of two parallel conductors of infinite length and placed 1 meter apart in vacuum causes each conductor to experience a force of 2 into 10 to the power minus 7 Newton per meter of length of the conductor. We can say that is equal to 1 ampere current. Now torque experienced by a current loop. So here we consider a rectangular loop in a uniform magnetic field. So let theta be the angle between the plane of the loop and the direction of the magnetic field. The axis of coil is perpendicular to the magnetic field. So here the force FSP can be written as L into B cross magnetic field B, or magnitude of force SP is L into B sin theta. In the same way, force QR is L into B cross B, or the magnitude of FQR is LB sin theta. So the forces FSP and FQR are equal in magnitude but opposite in direction, and they cancel out each other. Moreover, they act along the same line of action and hence do not produce torque. Now forces FPQ and FRS being equal in magnitude but opposite in direction cancel out each other and do not produce any translation motion. But they act along different lines of action and hence produce torque about the axis of the coil. So FPQ is I into L cross B, or magnitude of FPQ is BIL sine theta, where theta is 90 degree. So sine 90 is 1. We get FPQ is equal to BIL. In the same way, the force FRS is again BIL. So the torque experienced by the coil is torque is equal to force into perpendicular distance. So force is FPQ, that is BIL, and the perpendicular distance is Pn, which is B cos theta. So we can write torque is equal to BIL into B into cos of theta. So length into breadth is area. So we get BIA cos of theta. So if we have n number of turns, then we get torque is equal to BINA cos theta. And if phi is the angle between the normal to the coil and the direction of magnetic field, then phi plus theta is 90 degree. So theta is 90 minus phi. So torque can be written as IAB cos 90 minus phi, or torque is equal to Bina sine phi. One must be very careful in using the formula in terms of cos or sine, since it depends on the angle taken, whether with the plane of the coil or the normal of the coil. So torque in vector form. So we know that torque is equal to Bina sine phi. So we can write torque is equal to NIA B sine phi n cap, where n cap is unit vector which is normal to the plane of the loop. So we can write torque is equal to Ni A cross B, or torque is equal to N vector M cross vector B, since vector M is I into A, which is magnetic dipole moment. So the coil will rotate in the anticlockwise direction. So from top of the view, according to the figure, if we see, so the coil will rotate in anticlockwise direction about the axis of the coil shown by the dotted line. The torque acts in the upward direction along the dotted line. If phi is 0 degree, then torque is 0. If phi is 90 degree, then torque is maximum, that is Tmax is equal to Bina, B-I-N-A. And the unit of magnetic field B is Tesla, I is in ampere. So the above formula for torque can be used for any loop irrespective of its shape. Thank you.